All right, hello everybody. I would like to restart from where we left last time, and in particular give a quick review about model analysis. We said that this is a method that we use to simplify the solution of problems of systems that have more than one degree of freedom. You already have all the notes that I uploaded on Canvas with all the steps that we have to use in order to perform model analysis. Here we saw this example where we have these two, this first pendulum, this second pendulum that were connected to each other through this spring. And in this case, of course, we started by looking at the free body diagram of the first pendulum, the free body diagram of the second pendulum, so that we were able to write the equations of motion. So once we have the equations of motion, in this case we had also the values of the length, the two masses, the distance between the swinging point and the point where the mass was attached, and then also the k of the spring. So we plug the numbers, we wrote the system in matrix form, where we have the mass matrix, the acceleration vector, the stiffness matrix, the displacement vector. Of course, this is a free system, so we don't have anything on the other side of the equation. And then we start by looking at all the steps. So we calculated this first matrix first by looking at the mass matrix, and then we calculated the k tilde by doing simple algebraic calculations, matrix calculations. And then we can calculate first the natural frequencies. So the natural frequencies are calculated by solving this equation here. So we have lambda, which is our unknown in this case, I is the identity matrix, and then k tilde is the matrix that we just found, that we calculated before. So we can calculate the determinant of this matrix, and then we come up with this lambda 1 and lambda 2. Once we have lambda 1 and lambda 2, we can calculate the square root of these two quantities, and the square root of these two quantities will be our natural frequencies. Very important parameter that we need to look at. Then we can look at the eigenvectors. In this case, we have to solve this relation for the first eigenvalue and then for the second eigenvalue. Once we plug the first and the second eigenvalue in this relation, for the first eigenvalue we find the first eigenvector, for the second eigenvalue we find the second eigenvector. Remember that in this case we come up with always with two equations that are the same equation, which means that we need to, since we still have two unknowns, we can arbitrarily choose one unknown and then we can calculate the second accordingly, which is what we did here. So in this case, with these two equations, we decide that the first value of the eigenvector will be equal to 1. So in this case, the second one will be 1 as well. So this is how the eigenvector looks like. We can normalize the eigenvector, which means that we divide every element by the module of the element of the vector itself. So the module of the vector will be the summation of this one, and then squared and then square root. So 1 over square root of 2, 1 over square root of 2. We do the same thing with the second eigenvalue, so that we can find the second eigenvector. And this is the second eigenvector. After that, we can find the P matrix, which means we basically put together the two eigenvectors. Then we find the S matrix. Then we recall the m to the power of negative 1 over 2 matrix multiplied by P, which is what we have here. And then we find this this S matrix. We can also find the inverse of this matrix, so S to the power of negative 1, by using this relation here. P transpose, we take this one and we switch rows and columns. In this case, when we switch rows and columns, nothing changes, so they're the same. And then we multiply by m to the power of 1 over 2. And then we find this one. That's the step number 6, consists of introducing the initial conditions in modal coordinates. So these are the initial conditions in physical coordinates, because we have theta of 0 and theta dot of 0. Remember that we are looking at a rotating system, at the rotating elements, because the variable that we are looking at is the rotation of the first pendulum and the rotation of the second pendulum. So when we look at theta, here we have physical coordinates. So initial displacement, initial velocity. Once we have this initial displacement and initial velocity, we can convert in modal initial conditions. So we have the initial position in modal coordinate and the initial displacement also in modal coordinate. How do we do that? We take this matrix here, which is the one that we found before, and we multiply by the initial position in physical coordinate to find the initial position in modal coordinates, and in this case we had the initial velocity in physical coordinate is 0, 0, so the initial condition in modal coordinate will be 0, 0 as well. Once we have the initial conditions, we can find the equations in modal coordinates, so the modal equations, which means that we have every equation that is independent from, so all the equations are independent from each other. So we can use R1, R2 to indicate the different modal coordinates. And we already know that the general form of the equation will be the acceleration plus the square of the natural frequency times the displacement. So we can write this for the first one and the second. We already know how to solve a simple second order differential equation, because we saw when we were looking at simple harmonic oscillator. So we can find a solution for the first one and the second by simply looking at the natural frequency, the first and the second, and the initial conditions. We can actually simplify significantly both the equations in modal coordinates, and then once we have the equations in modal coordinates, we can switch back to the physical coordinates by using the S matrix. So theta t is equal to S times RT. RT is the vector that has basically the two solutions, and S is the matrix that we found before. By doing this one, we can find that these are the two solutions of our system in physical coordinate. As you can see, and also as we said last time, the process seems a little bit complex. It is actually not complex, but is actually simplified, because here usually the hard part of solving a problem is to solve the differential equation, but here we can we reduce the problem to independent differential equations, which means that the problem is significantly simplified. So with that said, the next step would be to expand this concept from 2 degrees of freedom to multiple degrees of freedom. Now, as you can imagine, the expansion from 2 to multiple degrees of freedom is pretty straightforward, because all the steps that we would follow are exactly the same. We will need to go through finding the equations of motion. We will need to go to so the equations of motion, and then from the equations of motion, if we have the numbers, we plug the numbers, otherwise we keep going with symbols, and then we go with all the steps. Again, they're pretty mechanical steps, because it's pretty much linear algebra, so we need to do calculations with matrices. The only difference that we would have when we work with 3, 4, 5 degrees of freedom instead of 2 is that we need to deal with bigger matrices. So in this case, for example, if we look at the mass matrix and the stiffness matrix, these two matrices are both 2 by 2 because our system is a 2 degree of freedom system. If we deal with a system that has 3 degrees of freedom, our mass matrix will be a 3 by 3, the stiffness matrix will be a 3 by 3. If we work with 4 degrees of freedom, of course we will have 4 by 4, 4 by 4, and so on. So this is the only difference that we have when we work with 2 degrees of freedom versus multiple, so 3, 4, 5 degrees of freedom. Of course, when we look at the eigenvector, when we look at the natural frequencies, if we have 3, 4 degrees of freedom, we will have 3, 4 natural frequencies. When we look at the eigenvectors, instead of having 2 elements, we will have 3, 4 elements, and so on. When we look at the equations, we will end up with 3, 4 equations that are still independent from each other when we work with model analysis. So this is again what makes model analysis very, very useful to solve this type of problem. And then we will have the response in modal coordinates. Again, if we have 4 degrees of freedom, we will have 4 responses, 1 for each degree of freedom. And then eventually we can go back to the physical coordinates by using the S matrix. So again, not much difference between working with 3, 4 or more degrees of freedom rather than 2. We just need to work with bigger matrices. Of course, in this case, we will work with software, Mathematica, MATLAB, Python, that can help us in, solving all this, going through all these calculations. So the next concept I would like to go over is the concept of continuous systems. So as you can see, we went from single degree of freedom problems to 2 degree of freedom problems, and then from 2 degree of freedom problems we went to multiple degree of freedom problems. Now the next step is to work with continuous systems. All right, when we work with continuous systems, actually the change that we see in comparison with discrete systems, that are the systems that we analyze so far, the change is pretty significant because, and now I'm going to write down like a little table that can help us to understand these differences between discrete and continuous systems. So when we talk about so let's work with looking at this comparison between discrete and continuous systems. So discrete systems are the systems that we analyzed so far, and we saw that we can work with rigid masses that are connected together through different elements. We worked with springs and dampers. So examples of discrete systems are, for example, the simple harmonic oscillator, where we have one mass and one spring. So this will be a discrete system. Or we can have, for example, the pendulum is also a discrete system. Or another example of discrete system would be the car with the suspension. When we isolate the body of the car, from the wheels, and we connect them with the springs. So in this case, of course, we still talk about discrete system, because we consider the body of the car as a rigid body, and then we consider the two wheels as two rigid bodies that are connected to each other through these springs. Of course, we can add the dashpots as well, but these are still continuous, discrete systems, all these. When we look at continuous systems, in this case we don't talk about rigid bodies anymore. in this case, we talk about flexible bodies. So flexible bodies means that they can undergo a certain deformation, and the most simple example, this is what we will start to look at today, is for example the string. So if I have, let's say, a string connected between 2 points, this string can deform, so it can vibrate, because now we're going to introduce the time, the concept of the time, of course. So again, an example could be the string that can vibrate, so it can displace up and down, or we can look, for example, at a beam. Even for the beam, we can look at the displacement in the vertical direction in this case. And again, these are called continuous systems because here we are not going to be able to distinguish the single degrees of freedom. We cannot distinguish a finite number of degrees of freedom because every single point of our string in this case, or beam in this case, will be able to vibrate, to oscillate, in this case in the vertical direction, but we are going to deal with an infinite number of degrees of freedom. So of course, if we have an infinite number of degrees of freedom, we cannot use the same tools that we have been using so far by looking at the free body diagram of each degree of freedom and then look at all the equilibrium equations. Of course, we cannot do that. So again, we are going to use different tools, the different methods that can help us in understanding and solving problems with continuous systems. Now, when we talk about discrete versus continuous systems, we need to look at some main differences between the two. So let's put a line here. So the very first difference is given by the variables that are involved. So when we talk about discrete systems, there is only one variable involved, which is time. Because if you remember, even if we had 2, 3, 4 degrees of freedom, for each degree of freedom, we were looking at the displacement as a function of time. We said, okay, the first mass will have this response, which was like x1 of t. The second mass had this response, which was x2 of t, and so on. But all these functions were functions of time only. Now, when we look at continuous systems, this is not true anymore, because instead of having only time as a variable, we have time and space. We have these two variables. So let's go back to the string example, and we can think about this concept of having both time and space. Because, for example, I want to know the displacement of this string. I want to know the displacement of this point of this string. So this point will have a certain motion, which will be a function of time. But this other point, we will have another response that will have another function of time. So that's why every point of the string will move by following a certain function of time. That's why we have time and space as variables, because again the response will change for every point of our string. It is the same, of course, if we look at a beam and so on. Something that we already talked about is the number of degrees of freedom. When we look at discrete system, we have a finite number of degrees of freedom. We have 1, 2, 3, 4, 5, but it's a number. we can say how many degrees of freedom we have if we look at a discrete system. On the other hand, when we look at continuous systems, the number of degrees of freedom is infinite. So infinite means that every point, we can divide this string in an infinite number of points. That's why we have a continuous function starting from one end to the other one, which means we have an infinite number of points, which means we have an infinite number of degrees of freedom. Now, the main consequence, I would say, of these two concepts, the fact that we have only time as a variable for discrete system and time and space as variables for continuous systems, and also that we have finite degrees of freedom and infinite degrees of freedom, is given by the type of equations of motion. When we're looking at discrete systems, the equations of motion are ODE, which means ordinary differential equations. Ordinary differential equations means that we have differential equations that only have one variable, which is the time. When we look at continuous systems, the equations of motion are PDE, that are partial differential equations, which means that, as we said at the very beginning, when we work with differential equations, the solution is a function. In this case, the function is a function of time only. In this case, the function is a function of time and space. That's why they are called the partial differential equation versus ordinary differential equations. And then the way how we solve the problems, the way how we solve these equations. In this case, we use typically analytical method or numerical method. In this case, we use separation of variables. Or we can use the finite element method, for example. So again, the most important part is that we deal from now on with this continuous system that we will study. We will deal with partial differential equation, which means that the solution of the partial differential equation is a function of both time and space. So, as we said before, the most simple continuous system that we can study is the string. So, when we look at the string, you can think about the string of a guitar, for example, and in general, the way how a string vibrates is governed by a very specific equation, which is the wave equation. Now, there are different forms of the wave equation depending on looking at one dimension or two dimensions, for example. When we look at the string, we look at the one-dimensional form of the wave equation. I'm going to write the equation first, and then we will see how we obtain the equation. Also because when we look at partial differential equations, they can be written in slightly different ways that are actually or equivalent to each other. So the first way we can write the wave equation is the following. So this is UTT, so we use the double subscript T equal to C squared times UXX. So in this case also we use the double subscript X. Or we can also write the equation as follows. This is just a different notation. It's the same, the exact same meaning, but a different notation. So in this case, we have d squared u in dt squared equal to c squared times d squared u in dx squared. There is actually a third way, a third notation to write in general a differential equation, in this case a partial differential equation. So we will have u double dot equal to c squared times u double prime. So when we, again, these are three perfectly equivalent forms of the exact same equation. We just write them in a different way. What does it mean? Here we have the second derivative of u, which is our function. U is the displacement function. In this case, with respect to time, is equal to this constant c, and we will see in a little bit what this constant is. So this constant square multiplied by uxx, which is the second derivative of the function u, the same function, displacement function, with respect to the variable x in this case. Very similarly here, we have the second derivative of the function u with respect to time. We use a double dot to indicate the second derivative with time, equal to c squared times u double prime, where this is the second derivative with respect to space, so with respect to the variable x. But again, these three notations are perfectly identical. Now, this equation is an equation that can be found in numerous phenomena, numerous physical phenomena. So, for example, it can be found in acoustic. Again, if you think about the way how the wave propagates, the sound wave propagates in space, or even in a string, like we will see in a little bit, is governed by the wave equation. In that case, this constant here, c, would be the, the speed of sound. Another case where we can find this equation is, for example, in optics. Even in optics, the way how the light propagates in a certain medium is also governed by this wave equation. In that case, c, the constant c, will be the speed of light. Will be the speed of light. Or, for example, if you take a rock and you throw in a lake, you will see that the water will start to form waves. In that case, they are like two-dimensional waves. So the equation will be slightly different, because instead of having only the second derivative of the displacement with respect to x, so one spatial coordinate, we will have two coordinates. We will have x and y, for example. But the equation is still the wave equation. Again, we can expand this to 2 dimensions, 3 dimensions, but the concept will be the same. The equation that we see here, again, these three forms of the exact same equation, are related to propagation of a wave in one direction only. So I would like to, as I said before, I wrote the equation, but now I would like to see which steps are needed in order to obtain this equation. So we can look at a very simple schematic where we have our string that is connected to, at the two ends at 2 points. So now we are assuming that the dotted, So the dotted line would represent the undeformed configuration of the string. The continuous line would represent the deformed configuration of the string. So what we want to do, we want to determine the displacement of the string, which means that we want to determine our function, which will be u as a function of x and t. So as we said before, when we were in the previous page, this point will displace with a certain function, in time. Here, this point will also follow a certain function, to displace in time. So we will have another u, and this is valid for every point along, the string from the very beginning to the very end. So we can also put coordinates. So we'll have that here x is equal to 0, and we can put that here x is equal to L, where L, of course, is the length of the string, and then u is the displacement in the vertical direction. Also, very soon we will look at a few assumptions that we make in order to solve this problem and find the wave equation. But for now, we can focus on the fact that we are looking at only the displacement of each point in the vertical direction with respect to this coordinate system. So we'll have x, which is our coordinate for determining the location of each point of the string, and then y is the direction in which the displacement of each point of the string occurs. So in order to derive the equation, the wave equation, as always we start from our Newton law. Summation of forces is equal to m times a. Of course, we need to see how we can adapt this to our continuous system. So instead of looking at the entire string, we can look at just a simple small infinitesimal portion of the string. So if we have our horizontal axis, we can take 2 points. Of course, I'm going to exaggerate, but we need to imagine that we are looking at just an infinitesimal portion of the string. So that infinitesimal portion of the string starts from location x, and then it ends at location x plus delta x. And then, of course, it can have a generic orientation. Now it's time to look at the assumptions. I'm going to write them down here. So assumption number 1 is that the gravity for us is negligible. So the gravity is negligible, and it makes sense if we consider that we have enough tension in the string, because, for example, if you think about a guitar, if you turn the guitar, upside down or, wherever you want, the sound doesn't really change, when you play the guitar. And this is because we have enough tension in the string so that the gravity becomes negligible. And then we can be under this assumption that, again, the gravity is negligible. The second assumption is that we have small deflections. So small deflections means that the deflection, so the displacement of each point of the string with respect to the original point is small in comparison with the entire length of the string. And then the third assumption that we can make is that we have uniform tension along the entire string. So the tension that is the force that we can see coming out when we make a cross section from the string is the same in every point. So you have a uniform tension. Now that we went through these assumptions, again here for the second assumption, I wrote small deflections. Here the drawing is, of course, the schematic is exaggerated because I need to highlight the two different points and the deflection of the points. But of course we have to imagine that we have very small deflections. So same thing now in the next schematic that I'm going to draw. So now again I'm going to make it even bigger to highlight all the different variables that we need to look at. Even in this case we start from x and we end at x plus delta x here. And then we have our piece of the string that starts from point x and ends at x plus delta x. As we said, we have tension coming out of the string on both sides. So we have t here and we have t also here. We said the tension is uniform over the entire string, so the value of t here is the same value of t here. So we need to look also at the angles that we have. Here we have a certain angle theta between the tangent of the string and the horizontal direction. And here also we have another angle that we can call theta plus delta theta. So now that we have this new schematic where we highlighted the forces that are in the string and also the angles, we will need this one to determine the direction of the displacement. We can look at each side of our equation f equal to m times a. So we can introduce a new quantity, which is the linear density that we indicate with the Greek letter rho. So this we can call so the linear density can be defined as the ratio between the mass of the string and the unit of length. So in mathematical form we can express this as rho equal to m, which will be the mass, divided by delta x. Of course, if here we have x and here we have x plus delta x, it means that this length here is delta x, and then the mass would be the mass of this piece of string. So we have that the linear density is equal to m divided by delta x. From this expression here, we can obtain actually the mass. So we have that the mass is equal to the product between density and linear density and delta x. Now, the second thing that we have to consider is the acceleration, because if we look at our equation f equal to m times a, so far we took care of this m here. We have to take care of the acceleration. So we know that the acceleration is the second derivative of the displacement. We indicated in our previous page the displacement as u. So if u is the displacement, again, we can indicate the acceleration as u tt, or as we did in the different forms, also I can put between parentheses u double dot, or which is the same of d square u in dt squared. Again, these three forms absolutely equivalent. So when we look at this form here, this side of the equation, m times a, with what we found so far, we have that m times a will be equal to rho delta x, which is m, times a, which is our acceleration. So the second derivative of the displacement with respect to time. So now that we took care of the right side of the equation, now we have to look at the left side of the equation. So we have to look at all the forces that are involved in this in this piece of string. So the summation of forces. So summation of forces, of course, we look at the forces in the y direction, so in the vertical direction. So this is x and this is y. We look at the forces in the vertical direction because we said that the displacement occurs in the vertical direction only. So basically we have to look at the vertical component of this force here and the vertical component of this force here. So a summation of forces in the in the vertical direction will be equal to t sine of theta plus delta theta minus, in this case we have that t is pointing a little bit upward, so we have that the component in the vertical direction is a positive component. Here the tension is pointing downward, which means that which means that the y component, the vertical component, is negative. So we have minus t sine of theta. So as you may recall, we need to write the function as a function, we have to write the displacement as a function of the time, but also as a function of the horizontal coordinate. So we can manipulate this a little bit. So instead of working with sine of a certain angle, if the angles are small, and we said the angles are small because we look at small deflections, we can work with the tangent of the angle, because we know that tangent is sine over cosine. If cosine is 1, tangent is equal to sine. So we can rewrite this, we can write as f equal to t, we can put in common between the two terms, and then we can have the tangent of theta plus delta theta minus the tangent of simply theta. Now we know that the tangent is basically the ratio between delta y and delta x. That's why we're using tangent, because we need the relation between the vertical displacement, which will be our delta y, and the change in the horizontal direction. So since we can introduce this tangent. So basically the tangent is nothing but the derivative of the displacement with respect to the horizontal direction. So we can rewrite this expression as follows. So we have that f is equal to t that multiplies, again, instead of using the tangent, we can use the derivative. So we have the derivative of u with respect to, so du in dx of x plus delta x and t, because we know that this is a function of time as well, minus du in dx at location x and also time t. So now that we have basically the right side of the equation and the left side of the equation, I'm talking about this equation, f equal to m times a, we can actually put them together. So when we put them together, we have the following: rho delta x and then u tt equal to t, this is the tension, du in dx, x plus delta x and t minus du in dx, which is also a function, of course, of the coordinate x and the time t. We can slightly rearrange this because we want to have basically this term on one side and all the other terms on the other side. So in this case, we obtain the following. We obtain u tt equal to t over rho delta x, and then what we have between parentheses actually remain the same. du in dx, x plus delta x and t minus du in dx and then x and t. So, as we said, we are working on a very small portion of the string. It is an infinitesimal portion of the string, which means that now we can take the limit for delta x that goes to 0. So we can have that u tt is equal to limit for delta x that goes to 0 of this quantity here. So we have t over rho delta x, and then we still have the quantity between, parentheses. I'm not gonna rewrite all it, but this is what we have. So this quantity t over rho can be placed outside of the limit. So we have utt equal to t over rho, because of course t and rho, they are not function of x, so they are constant, so they can go outside of the limit. So we have limit of 1 over delta x, and then we still have the quantity between parentheses. So now when we take this limit for delta x that goes to 0, we actually are working on calculating basically the derivative of this quantity here with respect to x. This is already the derivative of this function with respect to x. So if we derive one more time, what we obtain is simply the second derivative of this function with respect to x. So in this case, so when we calculate this limit, basically we remove the limit and we convert this to the second derivative of the displacement with respect to x. So with this one, the entire equation becomes utt equal to t over rho times, again, all this quantity here, the limit for delta x that goes to 0 of 1 over delta x of this quantity here, it is simply the second derivative of the function u with respect to x, so with respect to space. So we can write as u xx. Now this quantity here is a constant, is t over rho, and we can recall this constant again a different way depending on what kind of system we are looking at. In general, from a mathematical point of view, we can call this as c squared. So if we call this c squared, and we will see later why, we have that utt is equal to c squared times u xx. Now this is the velocity again, and this is the same equation that that I wrote at the very beginning, because we have the second derivative of the function with respect to time equal to c squared times the second derivative of the function with respect to space. So now, of course, these two are equivalent. This is a little bit more general. This is specific for the string, but we can do a little bit of reasoning on this equation. So the first thing that we can say is that if we look at this equation here, we can see that the way how a wave propagates on a string depends mainly on two factors. The first factor is the tension that we have in the string, because we have t, but also depends on the density of the material itself. So if you think about the guitar, actually it's pretty obvious that when you adjust the tension of the of the string, the sound changes. But even if you don't change, if you have the same tension, let's say, on all the strings of the guitar, they have different linear density, so it means that the sound between one string and the other one is actually different. So again, that's why when we look at the very simple example of the of the guitar, of the string of the guitar, these two parameters can be quickly correlated with the sound that we hear, which means the way how the wave propagates along the length of the string. So, of course, every time we see an equation, we need to relate the equation with the physical phenomenon. Also, another thing that I would like to point out is that we can look at the units, actually, of this quantity here. So here we have a certain tension divided by linear density that we indicated with rho. So what are the units of tension and linear density? So when we look at the unit of tension, tension of course is a force, so the units are newtons. And then the linear density is kilograms over meter, because we said that it is a mass divided by a certain delta x we call the beginning, so it's a length, so it's measured in meters. Newton, of course, is a force, mass times acceleration, so we have kilograms and then meter per second square. And then, of course, these two will stay the same, so we have kilogram over meters. We can slightly rearrange, so we have kilogram meter over second squared times meters over kilogram And if we simplify this one, we can get rid of the kilogram, and then mm becomes meter square divided by second square. Meter square over second square is simply a velocity squared. So if you look at this quantity, this is the reason why we call this the velocity at which the sound propagates within the string. So today I wanted to give you again a little bit of introduction about these continuous systems, mainly the differences between discrete and continuous systems, what are the variables that we need to look at, and also a very simple, very first example of a vibrating continuous system, which is the string. So next time we will go over the solution of this wave equation for this case. Thank you very much.